Consider now evaluating a definite integral, the integral of g of x with respect to x between 0 and 1. Now, if we can't do that analytically, I want some numerical method to estimate that. So we'll start with a sequence of independent draws from a uniform random variable between 0 and 1. So these have density function which is equal to 1 on that interval between 0 and 1, and 0 everywhere else. So I want to work out that definite integral, integrating g of x with respect to x between 0 and 1. Well, g of x is equal to 1 times g of x. So if I think of this as a bit of a change of variable, so integration by substitution, then I can do that effectively as integrating g of the uniform u with respect to u between 0 and 1, and that's equal to the expectation of g of u. So what this means is that if I draw a uniform point between 0 and 1, then g of u, in other words, evaluating the function I'm trying to integrate g at a randomly selected point between 0 and 1, well, that's just a random variable. I have no idea what the distribution of that random variable is, and frankly, I don't care. But hopefully it's something I can work out. If I've got a statement for g, I can pick a random point and evaluate g at that point. But the crucial thing is, whatever that resulting random variable g of the uniform point is, it has expectation equal to the value of the definite integral I want. Now, the reason that's useful is we've got a whole mechanism to handle what will happen when evaluating averages of random variables when I know the population expectation that they're drawn from. And this is the real power of the weak law of large numbers. So in other words, if I can't integrate g of x with respect to x between 0 and 1, I can just pick a whole load of uniform points, evaluate the function g at those uniform points, add them up and divide by how many points I've got. And if my n is large, whatever g is, whatever the distribution of g of u is, I don't care, but I know that for a large sample, these things will converge to the same value. As n tends to infinity, the difference between the two sides will tend to 0, certainly. So what does this mean? Let me draw a picture of a distribution or a function I'm trying to integrate. I think that is just about a function. I don't think I've gone back on myself at any point. But it certainly is a crazy shape that wouldn't be easy to integrate. But the integral between 0 and 1 is that area in red. So I want to work out what that area is. So assuming that area is finite, and as I've drawn it, it is, then that area is equal to a rectangle of length 1 and height, called it f hat x, where f hat x is just the average value of the function over that integral. So I've sort of drawn in a rectangle of length 1 and height f hat of x. Now I've just done this by eye, but hopefully, give or take my bad drawing, you can see that those two things have the same area. So you can sort of visualize this by scraping away the solid red area that's above the rectangle and sort of using that to fill in the gaps where the rectangle goes above the line bounding the area I'm trying to estimate. So just imagine scraping the solid red in and filling in the two regions which are in the rectangle and above the line. Because what that's saying is that the estimate of the definite integral should be equal to just evaluate f at a uniform point, do that a lot of times, work out the average of those, and that should give me an estimate of the function value over 0 to 1. So a nice example of that is integrating 1 over 1 plus x squared with respect to x between 0 and 1. So what I've done here, I did this visually just in Excel. So the first 5 columns, so column A to column E, contains 20 realizations of uniform 1. So they're all between 0 and 1. On average, half of them will be below 0.5, half above 0.5, and so on. And what's in the other columns, so G to K, is 1 over 1 plus the uniform point, where they kind of correspond across. And by that I mean, if I pick the top left uniform point, it corresponds to the top left of the second bit, the G to K part. So you can hopefully convince yourself of that the values in the left-hand section, which are close to 1, will have corresponding values close to 0.5, which is 1 over 1 plus 1 squared. The values in the left-hand part, which are close to 0, will have values close to 1 over 1 plus 0 squared, i.e. close to 1. So I pick out another value, hopefully you can see those. So just, if you're not quite sure what I'm talking about, just pause it at this thing and maybe grab a calculator and just check those values. So what this does mean is that if, for example, if I just take 20 points, so I average the first column of this, so G1 to G20, average those, and I got 0.7417. I then repeated this averaging column G and H, then GHI, then GHIJ, then GHIJK. And you can see my estimates are actually slightly increasing with the sample size. In general, they won't. They're no more likely to increase or decrease. What that says to me is probably column G was underestimating it a bit. And as my sample size got larger, it was pulling it more towards the correct value. Now, if you know a little bit of trigonometric integration, you might know that the integral of 1 over 1 plus x squared is basically an arctan function, inverse tangent function. So arctan of 1 minus arctan of 0 is pi by 4. And pi by 4 is about 0.7854. So yeah, in fact, the closest estimate to the true value was that based on the largest sample. And that's maybe what we would expect.